Welcome to AP Chemistry. We're looking at AP F25 Week 3A. What we're looking at in particular is in Unit 1.5. And here we want to apply Coulomb's law to determine the relative sizes of isoelectric species. And so here is Coulomb's law. The equation is the force of Coulombic attraction or repulsion is proportional to the nuclear charge Q1 and Q2 over the radius, or we can say the force of attraction is inversely proportional to the square between the two charged particles. And so we're going to kind of go over these isoelectronic species and define what isoelectronic species are. And so we notice that we have O2 minus, F1 minus, neon, sodium 1 plus, magnesium 2 plus. And so I drew a Bohr model of all of these species as written here. And then I wrote their charge, O2, not O2, O2 minus, so oxygen with the 2 minus charge. And we see that it has 8 protons, and then it also has, if we count these, 10 electrons. Now, when we look at the electron configuration of oxygen, it would be 1s2, 2s2, 2p4. And we notice there's 2 plus 2 plus 4 electrons, meaning it would have 8 electrons. But because this is O2 minus, it has gained 2 electrons in its outer shell. And so, and the Bohr model shows this, but my electron configuration doesn't. So we change that 4 to a 6. And so now we see that its actual electron configuration matches the Bohr model that I wrote. And it also is consistent with this charge, because if it has 8 protons and 10 electrons, it should have a 2 minus charge. And now we see it's 2 plus 2, which is 4, plus 6 is 10. So it has 10 electrons, 8 protons, and a 2 minus charge. And that's where we're getting that from. Very similar for F1 minus. Here again, this is drawn with 10 electrons, but our electron configuration is consistent with that of fluorine, the atom. And fluorine has 9 protons, and a neutral atom of fluorine has also 9 electrons. And so we see this is 2 plus 2, which is 4 plus 5, which is 9. But if it's fluoride 1 minus, the reason why it became 1 minus is because it gained an electron. And so instead of being 2p5, it's going to be 2p6. And we notice something interesting happens, is that the electron configuration of both oxide and fluoride are the same. And so we would say these two species, even though they're different, one is oxide, one is fluoride, they have the same electron arrangement around their nucleus, and they have the same electron configuration. And when this is the case, we say these are isoelectronic species. All right, and so we can also look at neon. And neon has 10 protons and 10 electrons, and it is a neutral charge. And this is drawn already there. And if you look at its electron configuration, it has 2 plus 2, which is 4 plus 6, which is 10 electrons. It already, we don't need to change anything because this is a neutral atom of neon, and this is the electron configuration of neon. And we see, once again, that this neon, even though it's not fluoride or oxide, has the same electron configuration as oxide and fluoride. They all three have a different number of protons, which makes them all 3 different elements. If we look at the sodium ion, and again, I'm drawing this with 10 electrons in here, this picture. So, but the electron configuration I'm showing as sodium, the atom, and it is 2 plus 2, which is 4, plus 6, which is 10, plus 1, which is 11. So a neutral atom of sodium would have 11 protons and 11 electrons, and this would be its electron configuration. But we're not writing the electron configuration for sodium, we're writing it for the sodium ion. how does it become a 1 plus charge? Sodium becomes a 1 plus charge by losing an electron. And something very interesting happens with cations. They don't only just lose an electron. Notice this: they lose an entire energy level. And so uh, now, instead of having 3 energy levels, it only has 2. And so, and what I mean by that is this is the energy level, the big number, energy level 1. That's energy level 2. That's energy level 2. That's just s orbital and p orbital, but both energy level 2. So it lost an entire energy level. And so now we notice after it loses this electron that it has 11 protons, 10 electrons, and it would have a positive 1 charge. But also we notice that it has the same electron configuration as all these other species. And so we say that it is isoelectronic with these other species here. They are not the same. This is sodium ion, that's neon, that's fluoride, that's oxide. But since they have the same electron configuration or the same electron arrangement around their nucleus, we say that they are isoelectronic. And then we look at magnesium. And magnesium, again, I'm drawing this as the magnesium ion. But the electron configuration is that of magnesium. We see that magnesium, the atom, has 12 protons, and a neutral charged atom should have 12 electrons. And this electron configuration is showing that for a neutral atom. 2 plus 2 plus 6 plus 2 is 12. So this configuration would show that it has 12 protons, but also 12 electrons. But if it's the magnesium ion, it has to lose 2 electrons. And it not only loses 2 electrons, notice the 2 is going to go away, but when it does that, it loses that 3rd energy level. And so we end up with this configuration. And sure enough, there's 10 electrons there. And it has the same electron configuration as all of the other species listed. And so because all of these atoms, all of these species, we're not going to call them atoms because some of them are ions, all of these species are different, but what they have in common is they have the same electron configuration or the same electron arrangement around the nucleus. Now, because they are different in that they have a different number of protons. We all notice this. So we have to determine here, all of these species share the same electron configuration. Hopefully we now know why. Which of these species has the smallest atomic or ionic radius? Provide a detailed explanation for your choice, explicitly referencing Coulomb's law. So Coulomb's law, we see this force of attraction between, there's a direct relationship between the force of attraction between the nucleus and so the higher the nuclear charge, there's a directly proportional relationship between the nucleus and the valence electrons, or all the electrons in the atom. And so what we look at in particular when we're looking at the size of the atom is we're looking and focusing on those valence electrons and the attraction those valence electrons have for the nucleus. And we can kind of come up with a number for this nuclear charge to determine what this relative force of attraction will be. We're not going to calculate an actual force, but we can say if this number here in the numerator were higher, then so would the force of attraction. Now we're going to leave R kind of out of this because we're not using this equation as like a mathematical equation. We're not going to say we're going to put a value in for R, because really right now we're saying all of these are the same size. And you just have to excuse that I didn't draw them to scale, but they were all the same size. They all have the same number of energy levels, and they all have the same number of electrons. So if we want to determine their size, we can kind of look at the pool these valence electrons as drawn have towards the nucleus. So how much is the nucleus pulling these electrons in towards them? The larger the force of attraction, then the smaller uh, the atom will be, because the pull will be stronger, meaning these electrons will be pulled closer to the nucleus. And so we have a formula for figuring that out, and that is called the effective nuclear charge. And the effective nuclear charge is just simply looking at Z, which is the number of protons, minus S, which is the number of core electrons. Now, we should know the difference between core and valence electrons. And I'm going to start with valence electrons. Valence electrons are the electrons in the highest energy level, or the outer shell of an atom. And so we can see on all of these have the same number of valence electrons. And the outer shell, and shell number 2, we have 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So they all have the same number of valence electrons. They also, so there we go, we can see that that's how we get valence electrons. We're just counting the outer shell. They also have the same number of core electrons. And core electrons are the number of electrons, or not the number, but is the electrons that are not valence electrons. So if they are not in the outer shell, then they are considered core electrons. So here we see 2, 2, 2, 2, and 2. So each of the energy level 1s have 2 dots representing 2 core electrons. Because these atoms are isoelectronic, they're all going to have the same number of valence electrons, and they're also going to have the same number of core electrons. Where they differ, the only place they differ, is that they have a different number of protons. All right, and so let's go ahead and apply our effective nuclear charge. And when we look at this oxide, we see oxygen has 8 protons, and then it would have 2 core electrons. And so we say the effective nuclear charge is 6. All right, and so that one would have an effective nuclear charge of 6. We go to fluorine, wrong equation there. Go to fluorine, we're going to see that it has 9 protons minus 2 core electrons, and that equals 7. And you will probably notice that oxygen is in group 16 or group 6A, and fluorine is in group 7A. Interesting, huh? So we see the effective nuclear charge of 6, effective nuclear charge of 7. So what we would say then is that because the effective nuclear charge, the charge within the nucleus, is less than that of fluoride, that the force of attraction between the protons in oxygen and the valence electrons in oxygen is weaker than the force of attraction between the protons in fluoride and the valence electrons of fluoride. And this is all determined by this numerical value. So we can see that because fluoride has a higher effective nuclear charge, that its pull will be, that its pull on the electrons toward the nucleus will be greater, and that atom will be indeed smaller. All right, so if we look at neon, we can do the same calculation. And for neon, we're going to see that it has 8 protons. I'm sorry, that's not true. 10 protons minus, and then 2 core electrons, which is 8. And that's where I got 8 from. So got a little ahead of myself. And so we see that this has an effective nuclear charge of 8. And that means the pull on these valence electrons, or the pull of these valence electrons towards the nucleus, is greater than that what we see in fluoride or oxide, even though those two things have the same electron configuration. And these are isoelectronic species. So they even have the same arrangement and everything, but the pull of these electrons is greater because the effective nuclear charge is higher. All right, we do the same thing with the sodium ion. In the sodium ion, now, normally we would say sodium is larger because it has a whole nother energy level. But what happened when it became the sodium ion? It lost an energy level. It has the same number of valence electrons and it has the same number of core electrons. And so what we look at then is the number of protons, and it's 11, and the same number of core electrons is 2. And so we end up at 9. And because 9 has a higher effective nuclear charge than 8, the pull on the valence electrons towards the nucleus is greater than that experienced by neon, fluoride, or oxide. And then we go to the last one, magnesium ion. And again, the magnesium ion, it lost the whole energy level. The electrons are held approximately the same distance. This is not assuming before we even talk about attraction. And we say, okay, well, this one has 12 protons, minus 2 electrons, and its effective nuclear charge is 10. All right, and so we can see that magnesium ion has the higher effective nuclear charge, which means that its valence electrons are going to be pulled closer to the nucleus, making the magnesium ion the smallest species. So this would be the smallest. Why? Because it has the highest nuclear charge. Right? This is the smallest atom or smallest species. It's not an atom, it's an ion. And then this would be, let's go ahead and put this in here. This would be the largest. And obviously, I'm not having you show any work on this. This is just my lecture for this one question, and help you gauge how to answer this question. All right, and so that's what we have there. So how can we answer this question? All right, so let's take a look at that real quick in light of all that we have. All right, and so let's move something over here. All right, there we go. And let's put this in here. All right. All right, so we need to make an explanation because you don't even have this option to show your work. I didn't want you to show your work. I just want you to explain. So it says, provide a detailed explanation for your choice explicitly referencing Coulomb's law. So magnesium ion has the smallest atomic radius. I want you to notice, first of all, I answered the question. Which has the smallest atomic or ionic radius? Magnesium. There we go. Now we're going to provide our detail. So always make sure you answer the question. Make sure it's very explicit for your grader, and then you can hopefully receive credit. So magnesium ion has the smallest atomic radius. We see that all species have the same number of electrons, but have a different number of protons. We notice this in our drawing. These all have the same number of electrons, 10 electrons, 10 electrons, 10 electrons, 10 electrons. They all have the same electron configuration. But what is different? Have a different number of protons. And so we see magnesium as the highest number of protons. And where do we find protons? That's correct, in the nucleus. And so when we say the nuclear charge, we're referring to those things that are in the nucleus. And it's no wonder that if it has more protons, that it's going to have a higher nuclear charge. All right, so all species have the same number of electrons, but have a different number of protons. Coulomb's law states that the force of attraction is directly proportional to the nuclear charge. Since magnesium ion has a higher nuclear charge due to having more protons, and that's what we noticed in our calculations, due to having more protons than other listed species, the force of attraction between the protons in the nucleus and surrounding electrons is greater, which makes it the smallest species listed. And so that thoroughly explains Coulomb's law. Hopefully, if you needed a refresher on nuclear charge or why that attraction is greater, that this video was helpful. But for now, thank you for watching. Please like and subscribe.